Hi, I'm Shiji Li. My project asks one simple question. Can a small open source vision language model act as a corrective expert for a robot? Behavior cloning is the easiest way to teach a robot from demos, but it has a well-known problem. When the policy makes a small mistake, it goes to a state that the demos never showed, and after that, it doesn't know what to do, like in the video here. DAgger fixes by asking an expert what to do at the states the learner visits. The problem is, we still need an expert that can label any state. My idea is to use a general VLM vision language model as that expert. The VLM looks at the same image the policy says, predicts a high-level command like approach cube or lift it, and a small handwritten controller turns the command into a low-level actions. On ManiSkill3 PickCube-v1, I test two hypotheses. The first one is vision language model DAgger reached the same performance as a handwritten finite-state machine expert, even though the vision language model never outputs a low-level action itself. The second one is the same vision language model can also output a progress score and use this score as a reverse shaping signal, gives further improvement on top of a strong baseline. I made 7 conditions. The policy is the same in all of them, a ResNet-18 plus 2-layer multi-layer perceptron, image only, with no access to simulator state. The two supervisors, the finite-state machine and the vision language model, both output one of 6 discrete labels per sect, and they share the same low-level controller, so the FSM versus VLM comparison is fair. The only thing that is different is where the label comes from. Condition A is the behavior cloning. Condition B is FSM DAgger, which use privileged state. C is vision language model DAgger with Tianwen 2.5 vision language model with 3 billion parameters and also with 6 class label space. Condition C v3 use 7 billion parameter Tianwen and a coarser 3 class label space and a separate higher resolution angled camera for the vision language model. Condition D, E, and E0 at the vision language model basis reverse weighting per sample on top of A and B. E0 is a alpha equals 0 control, same recipe with E, but with the VLM weighting turned off. Let me show the results. The first headline is the standard DAgger result. BC sits at 6% on 50 evaluation seats. Finite-state machine DAgger reaches 86%. That's a 26% point gain. Importantly, finite-state machine DAgger crosses the replay as policy reference of 80-12%. That is the success rate I get if I replay the demos themselves through the simulator. An offline trained policy usually cannot be that number because DAgger collects correction labels in states that the demos does not cover, and the policy learns to recover from its own mistakes. The per round rollout success goes up steadily from 33% in round 1 to 80% in round 5. So finite-state machine DAgger does exactly what the theory says. The next question is whether the vision language model can do the same. With the 3B Tianwen and the 6 class label space, condition C, I get 60%, no improvement over BC. The vision language model only opts 2 of the 6 labels, no matter what the image looks like. And the third DAgger round drops from 50% down to 17%. So I made 3 changes at the same time: a 7 billion parameter VLM, a coarser 3 class label space, and a higher resolution angle camera where the cube takes more pixels. This is condition C v3, and it gives me 80% success rate, closing 77% of the gap to finite-state machine. One important note. this condition is a mixed system. The vision-like model gives a coarse label from the image, but the small state-based sub-finite-state machine picks a sub-command at the runtime. So this is not a pure image-only result. What about reward shaping? Reward weighted BC on top of the finite-state machine DAgger condition E loses 12% points. The alpha equals 0 control E0 is important here. It cleanly separates the damage into 6 points of catastrophic forgetting from continuing to train on the demos, and another 6 points from the shaping rates themselves, pulling the policy in the wrong direction. The reason here is in the signal itself. 82% of the vision-like model's progress score fall into a single bucket, so the shaping signal carries almost no useful gradient. And so I think there are 3 things to remember in my project. First, classic DAgger works as expected, plus 26 points. Second, small open source vision-like models are not yet ready to use experts. They need a simpler label space and a better camera view to be useful. Finally, when the reward signal is bad, shaping does not just fail, it makes things worse. That's it. Thanks for watching.